Hello once again. In my previous video, I have discussed concepts with regards to the Otto cycle, the processes involved in the Otto cycle. And in this video, I want to discuss an example problem for an Otto cycle. So again, an Otto cycle is the ideal cycle for a spark ignition engine or a gasoline engine, wherein you have a spark plug. So we have discussed concepts, and now it's time to put in those concepts, and we will try to solve a problem. So let's read the problem. An ideal auto engine operating on the hot air standard, okay, with K is equal to 1.34. So K is 1.34. So K is normally 1.4, but this is hot air standard, and it is less than 1.4. Okay, so it has a compression ratio of 5. So I have discussed the isometric compression ratio. So yun ang ibig sabihin niyan. That's what is pertaining to the isentropic compression ratio, which is equal to V1 over V2. So that is equal to 5. Now, at the beginning of the compression, the volume is 6. So let's say V1. V1 is equal to 6 cubic feet. The pressure is 13.75 psia, and the temperature is 100 degrees Fahrenheit. So let us convert that. 100 plus 460, so we'll have 560 Rankine. Okay, during the constant volume heating, so let's write here QA, 340 BTU are added, okay, per cycle. So what is C? C is your percent clearance. So this is related to the clearance volume. I will explain this further as we solve the problem. Percent clearance. T3, that's the temperature at point 3. This is the pressure at point 3. E is the efficiency of the cycle. Efficiency. And PM, this is a new term. PM is the mean effective pressure. Mean effective pressure. Now, the mean effective pressure is equal to your work over the volume displacement. Okay, so let's review. Let's review our Otto cycle. So this is a cycle because it is composed of different processes that returns to the original state. Okay, so process 1 for an Otto cycle is an isentropic compression. So let's say this is point 1, this is point 2, and then you have the constant volume addition of heat. So that's a vertical line going to point 3. You have again an isentropic expansion going to point 4, and then from point 4 going to point 1, this is the rejection of heat. So we have here QA, we have here QR, rejection of heat. So from point 1 to point 2, we have the isometric compression ratio. It's equal to 5. So therefore, if V1 over V2 is equal to 5 and V1 is equal to 6 cubic feet, then therefore V2 is simply equal to 5. V2 would be equal to V1 over 5. Okay, so 6 over 5. Let's get our calculator. So we have 6 divided by 5. We have 1.2. So V2 is equal to 1.2 cubic feet. Okay, so what is C? Okay, percent clearance. Um, let us add a concept, no? So I've mentioned that from point 2 to point 3 is isometric process, and V2, okay, this one, V sub 2 is equal to V sub 3, but your V sub 2, this is V sub 2, is equal to C, that's the percent clearance, times VD, okay, which is the volume displacement. So again, volume displacement is equal to V1 minus V2. So we can derive, okay, we can derive our percent clearance from the isentropic compression ratio. So we have RK is equal to V1 over V2. Okay? So let's just say that V1, okay, V1, what if I add here or I subtract V2? So I should also add V2, okay, in order to maintain the equality. So you have V1 minus V2 plus V2. So V2 minus V2 is 0. So I still have V2, I still have V1 on my numerator. But V1 minus V2 is your volume displacement. Okay? V1 minus V2 is your volume displacement. So I will replace this portion with V sub D. Okay? So I have V sub D plus V sub 2 over V sub 2. Now, V sub 2, as I mentioned a while ago, V sub 2 is equal to the percent clearance times V sub D. So let us change this. Okay, let's substitute. V sub 2 is C times V sub D, and V sub 2 in the denominator is also C times V sub D. So V sub D can be factored out, and I will now have 1 plus C over C times V sub D. So what will happen is, I can cancel V sub D, and therefore R sub k is equal to 1 plus C over C. So this is a new formula that you should remember. And since we're given the compression ratio, okay, 5 is your compression ratio. So 5 is equal to 1 plus C over C. I can solve for C. Okay, using simple algebra, I have 5C is equal to 1 plus C. This will become 4C is equal to 1. Therefore, your C is equal to 1 over 4 or 0.25. Since this is a percent clearance, so therefore, C is equal to 25%. So I hope that is clear. Let's proceed with the other unknowns. So letter A is already known. Check. So B is T3 and P3. Okay? So here, we are now considering this point. So from point 2 to 3, remember that this is isometric process. So let us recall our isometric formulas. Okay? So process 2 to 3 is isometric, and since we are looking for pressure and temperature, we know that, so let's say we start with P1 V1 over T1 is equal to P2 V2 over T2. Since this is isometric, I will cancel the volume, and what I now have is P1 over T1 is equal to P2 over T2, or P2 over P1 over P1 is equal to T2 over T1. Okay? So this is just a small review. But since we are dealing with process 2 to 3, no, let us change our initial pressure P1 to a subscript of 2, and our final pressure, which is 3, to a subscript, our 2 here will become 3. Okay? So let us just applying it to this one, to the points, no? So therefore, this can be written as P3 over P2 is equal to T3 over T2. So this is our formula that is applied to to the problem or to the Otto cycle. Okay? So P3 and T3. So as we can see here, P2 and T3 cannot be solved. Pressure 3 and temperature 3 cannot be solved because we don't have essentially P2 and T2 yet. Okay? So we have to go back to the first process, which is process 1 to 2, the isentropic compression. Okay, so we will recall the isentropic formulas. So we have P2 over P1. P2 over P1 is equal to V1 over V2 raised to K. And V1 over V2 is your isentropic compression ratio. So we can have R sub K raised to K. So P2 is equal to P1. So P1 is given 13.75 psia, 13.75 psia, and our volumetric ratio, isentropic volumetric ratio is 5. Okay, that is given. So 5 raised to 1.34. So let me just check our K. Yes, 1.34. Okay, so we will get our calculator again, and we have 5 raised to 1.34, and then multiply that by 13.75. Okay, so the answer is 118.83. 118.83. 83 psia. So that is our P2. Now, how about our T2? So we have also learned that T2 over T1 is equal to V1 over V2, this time raised to K minus 1. So again, T2 would simply be T1. So T1 is 100 plus, this is 560. Let me just check. Okay, 560 Rankine. And then this will be again 5 R sub K raised to K minus 1. So this will be 0.34. Okay, so what is our T sub 2? Calculator again. We have 5 raised to 0.34, and then multiply by 560. Okay, so the answer is 967.92. 967.92 Rankine. So we have now P2 and T2. But this is still lacking. Okay? We need at least one more value, either P3 or T3, to solve for either one. So let's say I can solve for T3. I think I can solve for T3 because I already have T2, and I will do that by considering the added heat at 340 BTU. So the added heat, so we will go back again. Addition of heat is uh, through isometric process, or the addition of heat is constant volume. So, balik tayo dito, QA would be equal to MCV, and this is process 2 to 3, so this will become T3 minus T2, final temperature minus the initial temperature. So the initial here is the temperature 2, okay, because we're dealing with process 2 to 3. So we don't have mass yet, but we can solve the mass, okay, by the initial given P1, V1, and T1 actually. So since we have P1, V1, and T1, we can use the perfect gas law. PV is equal to MRT. So mass is equal to P1 V1 over RT1. Okay? So initial pressure is 13.75 pounds per square inch, and then volume Initial volume is given at 6 cubic feet. 6 cubic feet. And then R is 53.342 pound force feet per pound mass Rankine. Okay, so how do we know that this is air? It says here hot air standard, okay, with K is equal to 1.34. So the gas constant will remain the same, but the K, instead of 1.4, it's now 1.34. And then T1 is 560. 560 Rankine. So again, let us do some cancellation first. This is pound force. Pound force cancels out. Rankine cancels out. Feet here cancels out. So there remains a square feet. So what we need to do is have another conversion here to convert the square inches. Okay. So to convert that, we have 144 square inch is 1 square foot. Okay. So square inch cancels out, this cancels out. Square foot here will cancel out the square foot there. And the final unit would be in pound mass. Okay. So again, let us get our calculator. So we have 13.75 times 6 times 144. And then divide that by the product of 53.342 times 560. So the answer is 0.3977 pound mass. So what is C sub V? So we know C sub V is equal to R over K minus 1. So R is 53.342 pound force feet over pound mass Rankine. And then K minus 1, this is 1.34 minus 1. So calculator again, 53.342 divided by 0.34. So we have 156.89. 156.89 pound force feet over pound mass Rankine. So now that we have C sub V, we can go ahead. I think it would be better first to convert this to BTU. Okay, because our QA is in BTU. So we have 1 BTU is 778 pound force feet. Okay, so this one cancels out. And our C sub V would be 156.89, or this value divided by 778, 0.2017, 0.2017 BTU per pound mass Rankine. Okay, so from our Q sub A, we have MCV T3 minus T2. We can go ahead here and derive a formula for T3. So we have QA MCVT3 minus MCVT2. Therefore, T3 would be equal to QA plus MCVT2, okay, all over MCV. Okay, so QA is 340 BTU, that's the heat added. Mass is equal to 0.3977 pound mass. Multiply that by the CV, 0.2017 BTU per pound mass Rankine. And then multiply that by T2. So we have solved T2 a while ago. T2 is 967.92. And then this would be 0.3977 pound mass multiplied by the CV BTU per pound mass Rankine. Okay, so here pound mass cancels out, Rankine cancels out. So in the numerator, we have the unit of BTU, and in the denominator, we have the unit of BTU per BTU per Rankine. Okay, BTU per Rankine. So BTU will cancel out and the final unit is in Rankine. So let us solve for T sub 3. So let's get first this one, 0.3977 times 0.2017 times 967.92. Let's add 340 BTU. And we will divide that. Okay, we will divide this by the product of the mass times the C sub V. So I forgot to write here the value for C sub V. Anyway, we will divide that by the product of the mass, 0.3977 times C sub B, 0.2017. Okay, so the answer is 5,206. So 5,206.47. 47 Rankine. So let's just put here again 0.2017. Okay? So this is T3. So now that we know T3, okay? So check muna natin dito, T3, temperature 3, pressure 3. So pressure 3, we will simply use this formula. Okay, P3 over P2 is equal to P3 over P2. Let's solve it here. P3 over P2 is equal to T3 over T2. So P3 is equal to P2 times T3 over T2. Okay? So P2 is equal to, we have solved that a while ago. Ito, 118.83 psia. And then T3 is equal to 5,206.47. And then T2 is equal to 967.92. Okay? So remember, okay, this formula came from the isometric process. So simple lang siya. Okay? Cancel. And P3 will be equal to, so let's divide this by 967.92 and multiply it by 118.83. So we have 639.19 psia. Okay? So, check. Then we go with efficiency. So, as I've discussed, the efficiency of this cycle, okay, or generally, the efficiency of any cycle is equal to your work over the heat added. Then we multiply it by 100. So, again, work is equal to QA, the heat added, minus QR. So, all over QA. Okay, but we can, let's go ahead and simplify this formula first. So, our heat added, so we know that our heat added is equal to MCV, T3 minus T2. Okay, because the addition of heat happens at points 2 to 3. And then your heat rejected, okay, heat rejected or rejection of heat will happen at points 4 to 1. So actually your final point here is point 1. Okay, remember that. So we have MCV, okay, T1 minus T4 over MCV, again this is QA, T3 minus T2. So you notice here we can cancel the product of MCV. Okay, we can factor it out. and then it will be cancelled from the denominator. So what is left? So we can simplify it as T3 minus T2 over T3 minus T2 minus T1 minus T4 over T3 minus T2. Okay, distributing the denominator. So this one, since this is T3 minus T3 over T2 minus T2, okay, it will be equal to 1. Divide by itself. And then as we, then this will become T1 minus T1 minus T4 over T3 minus T2. Before we proceed with simplifying this equation, let us first consider this important factor, no? QR, heat rejected, will be a quantity that is negative by definition. Okay? So, it means to say that if I continue, let's say with solving a problem, this will really become negative. But the conflict here is you will subtract QA minus QR by the absolute value of QR. Okay? So, it means to say that T4 is greater than T1. So therefore, QR will be a negative value. But as I've said, we have to get the absolute value of QR. So therefore, I should rearrange for your QR to be positive. I should rearrange T1 and T4 so that this will become a positive answer. Okay? So, rearrange this. I should rearrange this. And it will become 1. It should become 1 minus T4 minus T1 over T3 minus T2. T3 minus T2. Okay? Now, the trick happens here. Okay? I could simplify this equation, okay, this efficiency in terms of temperature to a formula which is which is more simpler, which will be in terms of your R sub k or your isentropic compression ratio. So how will we do that? So first, remember that this is isentropic, no? T4, T4, T1. Let us check the points. Okay, check the points here. Okay, so T4 from point 3 to point 3 to point 4 is isentropic compression. Remember that. From point 1 to point 2 is isentropic compression, sorry. And from point 3 to point 4 is isentropic expansion. So both are in the isentropic process. So why is it important to to emphasize that? Because we will use the isentropic process formulas for us to simplify this matter. Okay? So, uh, remember that T2 over T1, as I've said, as we have derived, is equal to V1 over V2 raised to K minus 1. Or this would be R sub K raised to K minus 1. I have already shown that in solving for this one, in solving for T sub 2. Okay? So, T sub 2, T sub 2, this one, can be substituted by T sub 1 times R sub K raised to K minus 1. Okay? And then, how about your T sub 3? Okay? So, uh, let us uh, let us consider point this process going from 3 to 4. Okay? Remember, going from 3 to 4. Okay? So we have uh, T4 over T3, okay, is equal again to, in this case, V3 over V4 raised to k minus 1. Okay? But, no, what is the equivalent of V3 and V4? What is the equivalent of V3 and V4? Let's go here. V3 is equal to V2 and V4 is equal to your V1. Okay? V3 is equal to V2 and V4 is equal to V1. So this is raised to k minus 1. Your T4 over T3, if I will get the reciprocal, I should get T3 over T4 is equal to V1 over V2, again, raised to k minus 1. And V1 over V2 is R sub k raised to k minus 1. So therefore, T3 is equal to T4 times R sub k raised to k minus 1. So if I substitute it here to my formula of efficiency, 1 minus T4 minus T1 all over, so T3 is T4 raised to T4 times R sub k raised to k minus 1 minus T2, T2 is equal to T1 times R sub k raised to k minus 1. So in the denominator, I can factor out R sub k raised to k minus 1. And I will have T4 minus T1. And in the numerator, I have T4 minus T1. So what will happen is I can cancel T4 minus T1. And finally, the simplified formula for efficiency will become 1 minus 1 over R sub k raised to k minus 1. So you have to remember this formula so that the solution for efficiency will be very, very simple. So it is simply 5 raised to 1 minus 1 over 5 raised to 0.34. So we will get our calculator to solve for the efficiency. So we'll have 1 minus the quantity, 1 divided by 5 raised to 0.34. So the answer is 0.4214. 0.4214. So of course this is efficiency, and we should express this as in terms of percentage. So 42.4, 14%. Okay. So last in the unknown is the mean effective pressure, or the P sub M. And as I've said, P sub M is equal to work over V sub D. V sub D is the volume displacement. So let's replace it with V2 minus V1. So what we don't have here is the work, but from efficiency, we know that efficiency is equal to work over QA. So therefore, work is simply efficiency times your Q sub A. So our efficiency is 0.4214 and our added heat is 340 BTU. So work is equal to, so we just multiply this with 340 and we have 143.29. 143.29 BTU. Okay? So the appropriate unit that we should use here is in pound force feet, so that we will have a mean effective pressure in pounds per square foot. Okay? So we know that 1 BTU is 778 pound force feet. Okay? So if we multiply this by 778, we 111,478. 111,478.68. 68 pound force feet. So we go back again with the computation of P sub M. So we have 111,478 478.68 pound-force feet all over your V2 minus V1. So let us just recall what is our V sub 2. We have solved that 1.2 and our V sub 1 is 6. Okay? So of course, this will be the clearance volume. I have to correct myself. The clearance volume is actually V1 minus V2 because V1 is greater. So V1 minus V2. Okay. So let's just correct this. V1 minus V2. So 6 minus 1.2, and this is in cubic feet. So this will be square feet. So we have PSF, but since we started with the unit of PSIA, so therefore, since this is in PSF, we should convert the square foot here. No? We know that 1 square foot is 144 square inches. Okay? So square foot cancels out and we have pounds per square inches. So let us again get our calculator. So this value divided by 6 minus 1.2. So we have 23,000 and then divided by 144. So we have 161.28. 161.28 psia. So that is your mean effective pressure. So there you have it. That's an example problem of an Otto cycle. Thank you for watching and stay tuned for more problems.